Okay, so question number 3 now. It's interesting one. It's very straightforward when you know what you're doing, but essentially, if the sound waves are going down these two pathways and they're the same distance, then they're going to arrive in phase. If they're going down these two pathways and it's a different distance, then they may or may not arrive in phase, depending on the difference in the path length. So basically what this is saying, what we need to say is, as this pulls apart, of course, initially the path lengths are the same, both sides, so the waves arrive in phase and we have a maximum at point Y. However, as D2 increases, the path length in D2 increasis. So difference in length, and this is the maths that I worked out, is fairly straightforward really. If this bit is the extra there, and this extra bit there, we pulled it all out, so it's got that much longer, then the difference will be D2 minus D1, that's what that distance is, and there's two of them because it's gone through there and through there. So 2 lots of brackets D2 minus D1 is going to be equal to, well, let's start down here. It's going to be equal to a whole number of wavelengths where there's a maxima, and it's going to be equal to a half number of wavelengths, an uneven number of wavelengths when it's a minima. So I put here, that would be n lambda for maxima, 2 times D2 minus D1 times equals n lambda, where n is a whole number for maxima, and for minima it would be n minus a half brackets lambda would be equal to D2 minus D1. Now, you don't need to go into that to work this equation out or anything like that, but you just need to basically say a minima will occur when they are out of phase, by 180 degrees out of phase, or half wavelength out of phase, and maxima when they're in phase. Of course, now this next bit is saying calculate the minimum distance moved by the movable tube for the sound detected at Y to be a quietist. So we know the speed, the velocity, and the speed, so we can work out the wavelength, which is 0.42 meters. Therefore, the smallest path length that's going to make them go out of phase will be when the path difference is half a wavelength. So we want to get this number, divide it by 2, lambda upon 2 therefore is 0.2152. That's the path difference we want to achieve, and that path difference is going to basically occur, this is the weird thing, we're going to have to move the movable tube distance out, which is half of that, in order to get that as a total. Now, it's hard to explain, but if you think here, we're trying to get 0.2 meters, then if we move this thing out 0.1, we're going to move 0.1 there and 0.1 there, and so of course 2 lots of that will give us our change of wavelength. So hopefully you can see lambda upon 2 is 0.212, so we really want to cut that in half, so it's 0.01 meters. To determine the speed of sound, well, we'll start with these two being equal, D2 and D1. We'll increase D2 to measure successive maxima and minima, that makes sense. Now the increase in D2 between successive maxima will be given by 2 lots of delta D2, the change of length, is equal to wavelength, where it's a maxima, and between minima it'll be 2 lots of lambda upon 2, because they're going to be half a wavelength down. So between each maxima or minima, the difference in length will be lambda upon 4/4. And so once we basically know this, is the difference of that wavelength, it goes from maximum to minima, then it will go from maximum to minima over a quarter of a wavelength, and then over another quarter of a wavelength it will be back to maxima, and so on. So once we know the difference between maximas and minimas, we multiply that by 4, shove it into this equation, and we find the velocity.